What does it mean in quantum theory when two particles remain connected even after the entire universe seems to have moved between them? In laboratories around the world, physicists working within the framework of quantum theory observe pairs of particles created together and then gently separated, sometimes by meters, sometimes by kilometers, sometimes by distances large enough that light itself would take time to cross between them. When one of these particles is measured, its properties appear immediately correlated with the other, even though nothing visible travels between them. The particles do not glow or signal or tug. They simply respond as if the separation never fully happened. This is not something imagined or inferred. It is a direct prediction of quantum theory, confirmed in the clicks of detectors, in the quiet regularity of data, in results that repeat with careful consistency. Before anything deeper unfolds, you might gently take a moment to support this shared curiosity. If you enjoy these explorations, you are warmly invited to like and subscribe. We are quietly aiming to reach 1,000 subscribers by the end of January, and when that happens, $100 will be donated to UNICEF to help spread education and care to children who do not have access to the internet or basic resources. You are also welcome, if you wish, to leave a note in the comments about where you are tuning in from, letting that small detail rest alongside the science. At first glance, these correlated particles behave a bit like two gloves placed into separate boxes. If you open one box and find a left glove, you instantly know the other box contains the right glove, no matter how far away it is. But this simple picture begins to fall apart, because in quantum experiments, the gloves are not left or right until the moment you look. Before measurement, each particle does not carry a fixed property waiting to be revealed. Instead, both particles are described, together, as one shared quantum state stretched across space. This means the correlation is not something sent after the measurement. It is something that already exists as part of how the system is defined. The measurement does not create the connection, it exposes it. And once this is seen clearly, the existence of such correlations stops being a strange coincidence and starts to feel like an inevitable consequence of how quantum systems are allowed to exist at all. Once the initial surprise of these correlations settles, the next step is to understand what physicists mean when they talk about a quantum state. In everyday life, a state usually describes something definite. A coin is heads or tails. A light is on or off. But in quantum physics, a state is not a list of fixed properties. It is a complete description of everything that can be known about a system before a measurement is made. For a single particle, this state does not say where the particle is or how it spins in a definite way. Instead, it quietly encodes the range of possibilities and how likely each one is to appear if we choose to look. It is less like a label and more like a landscape of potential outcomes, smooth and continuous, waiting for interaction. When two particles become entangled, this description changes in a subtle but profound way. Instead of assigning each particle its own independent state, quantum theory assigns a single shared state to both of them together. This combined state does not belong to either particle on its own. It belongs to the pair as a whole, no matter how far apart they later move. A useful way to picture this is to imagine a single melody played on two instruments at once. You cannot describe the music by talking about either instrument alone, because the harmony only exists when both are considered together. The notes are not independent. They are defined by their relationship. In the same way, an entangled quantum state describes relationships between particles rather than individual attributes. This is why separation in space does not dissolve the connection. Distance does not divide the state, because the state was never located at a single point to begin with. It is an abstract but precise description that spans wherever the particles happen to be. And once this is understood, entanglement begins to feel less like a mysterious thread stretched across the universe, and more like a natural consequence of how quantum descriptions are written at the most fundamental level. A shared quantum state does not appear by accident. It is formed through interaction, through moments when particles touch the same physical process and, for a brief time, cannot be meaningfully described as separate things at all. In the physical world, particles are constantly interacting. They collide, decay, scatter, and exchange energy. Most of these interactions leave no lasting trace once the particles move on. But under the right conditions, an interaction can bind the quantum descriptions of two particles together, creating a single state that contains both of them at once. One of the simplest examples comes from particle decay. Imagine an unstable particle at rest that breaks apart into two smaller particles, flying off in opposite directions. Before the decay, there was only one system. After the decay, there are two particles, but certain quantities must still be conserved. Energy must balance. Momentum must add up. Angular momentum must remain whole. These conservation laws are not optional. They are built into the structure of physics itself. Because of this, the two new particles cannot choose their properties independently. If one particle carries away a certain amount of momentum in one direction, the other must carry an equal amount in the opposite direction. If one has a particular spin orientation, the other must be arranged so that the total spin matches what existed before the decay. The interaction has linked them in a way that cannot be undone by distance alone. At the quantum level, this linking is not stored as a hidden agreement or a set of instructions. It is written directly into the quantum state. The state does not say this particle has this value and that particle has that value. Instead, it says if one particle is found to have a certain value, the other will be found to have the corresponding one. The information lives in the relationship, not in the parts. A helpful analogy here is a pair of perfectly balanced dice cast together under a strict rule. The rule is that the numbers must always add up to 7, but the dice themselves are not labeled beforehand. Until you look, there is no fixed number on either die. Yet once one die is revealed, the other is immediately determined, not because it received a message, but because the rule was built into the way they were cast. The roll created a constraint that applies to both at once. In quantum physics, the interaction plays the role of that rule. It constrains the combined system so strongly that it no longer makes sense to talk about independent properties. The particles emerge from the interaction already sharing a single description. Entanglement can also be created when particles collide and scatter. When two particles approach each other, their quantum states overlap. For a short time, they are described by one combined state that includes both of them and the forces between them. If they separate again without fully disentangling, part of that shared description can remain. The details of the interaction, the symmetry of the system, and the way energy and momentum are exchanged all determine whether entanglement survives. Even particles that never directly touch can become entangled through a mediator. A photon can interact with two atoms at different times, leaving behind correlations between them. A shared electromagnetic field can link distant systems. What matters is not physical contact, but participation in the same quantum process. What is striking is how ordinary this is at the microscopic scale. Entanglement is not rare or exotic. It is a natural outcome of interaction. In fact, quantum theory suggests that the universe is constantly generating entanglement wherever particles interact, and just as constantly destroying it through interactions with the environment. This brings in an important idea. Entanglement is fragile. When an entangled system interacts too strongly with its surroundings, the shared state becomes diluted. Information about the system leaks outward, spreading into countless degrees of freedom. The clean correlations that once linked two particles become harder to detect, not because they vanish, but because they are shared with so much else. This process is known in physics as decoherence, though the name matters less than the intuition. The environment acts like a vast audience, silently observing the system. Each interaction leaves a tiny imprint, and together they blur the sharp quantum relationships that once existed. This is why entanglement is easiest to study in carefully controlled laboratory conditions, where unwanted interactions are minimized. Yet even with this fragility, entanglement persists long enough to be measured, tested, and used. Experiments routinely create entangled photons by passing laser light through special crystals that split photons into pairs. Atomic systems are cooled to near absolute zero, so their interactions can be precisely shaped. Superconducting circuits are engineered to share quantum states across microscopic distances. Each of these methods relies on the same underlying principle. A carefully designed interaction creates a shared state that cannot be reduced to its parts. What is important to notice is that entanglement does not require intention or observation. It happens whether anyone is watching or not. The universe does not pause to ask whether a correlation will be confusing. It simply follows its rules. When systems interact under the right constraints, entanglement is the natural result. This perspective removes some of the drama often associated with the idea. Entanglement is not a mysterious bond added on top of reality. It is what reality looks like when quantum systems are allowed to interact fully and honestly. Separation is something that must be actively maintained. Left to itself, the quantum world tends toward shared description. Once this is seen, the next puzzle becomes unavoidable. If entanglement is created through interaction and encoded in a shared state, what exactly happens when one part of that state is measured? How does a local act of observation reveal correlations that span any distance at all? And why does this revelation feel instantaneous, even though nothing physical seems to travel between the particles? That question waits quietly, ready to be examined next. When a measurement is finally made on one particle in an entangled pair, something very specific happens, and understanding it requires slowing down and looking closely at what measurement means in quantum physics. In everyday experience, measuring feels passive. You look at a thermometer and read the temperature. You glance at a clock and note the time. The act of observation seems separate from the thing being observed. But in the quantum world, measurement is not a gentle glance. It is an interaction, a physical process that forces a system to respond in a definite way. Before measurement, the entangled pair exists in a shared quantum state that does not assign fixed properties to either particle individually. The state contains possibilities, structured in a precise mathematical way, but none of those possibilities are singled out as real outcomes yet. The particles are not hiding values. They are genuinely undefined with respect to the property being measured. When a detector interacts with one particle, the system is forced to choose. The measurement device is large, complex, and deeply connected to the environment. It cannot remain in a superposition of outcomes. As it interacts with the particle, one of the possible results becomes actual, recorded as a definite event in the macroscopic world. At that moment, the shared quantum state updates. Not in space and not by sending a signal, but as a change in the description of the system. The state that once contained many correlated possibilities is reduced to a smaller set consistent with the observed outcome. Because the state was shared, this update applies to the entire system at once. The description of the second particle changes immediately, even if it is far away, because it was never described independently in the first place. There is no second step. There is no delay. There is only one state, and it has been refined. This is where the sense of instant correlation comes from. If the second particle is later measured, its outcome will be correlated with the first in exactly the way the shared state allows. It feels as though the first measurement reached across space and forced the second particle into a matching condition. But nothing traveled. Nothing was pushed or pulled. The correlation was already there, waiting to be revealed. A useful way to picture this is to imagine a carefully written contract that applies to two people at once. Before either person signs, the contract exists as a set of possible agreements. When one person signs, the terms become fixed, and those terms apply immediately to both parties, no matter where they are. The act of signing does not send a messenger to the other person. It simply finalizes a shared agreement that already existed. In quantum measurement, the detector plays the role of the signature. It finalizes one outcome from the set of allowed correlations. The update feels non-local because the agreement was non-local to begin with. This explanation is subtle, and it often feels unsatisfying at first because it clashes with deeply ingrained intuitions about cause and effect. We are used to thinking that influences propagate through space over time. We imagine arrows of causation moving from one place to another. Entanglement does not fit neatly into that picture because the correlations do not arise from influences traveling between particles after measurement. Instead, the correlations arise from the structure of the quantum state itself. The state encodes relationships that are not localized at points in space. Measurement does not create those relationships. It selects one of their possible expressions. This is why physicists are careful when they talk about collapse. The word can suggest a dramatic physical event spreading outward from the measurement site. But in modern interpretations, what collapses is not a physical wave traveling through space. It is the description we use to account for what has been observed. The measurement outcome is local. The detector clicks here, now. But the update too. The quantum state is global because the state was global. This distinction matters. It preserves consistency with relativity, which forbids faster-than-light signals, while still allowing strong correlations to exist. Experiments confirm this picture with remarkable precision. In carefully designed tests, pairs of entangled particles are sent to distant detectors. The choice of what measurement to perform on one particle is made randomly, sometimes after the particles are already separated. Yet the correlations appear exactly as predicted by quantum theory, regardless of distance or timing. Importantly, the outcomes themselves are random. No experimenter can control which result appears when measuring a single particle. This randomness is not due to ignorance or lack of precision. It is fundamental, and because the outcomes are random, they cannot be used to send messages. Even though the correlations are instant, the individual results contain no usable information on their own. Only when results from both sides are later compared does the pattern emerge. This comparison requires ordinary communication, limited by the speed of light. Until then, each observer simply sees a sequence of unpredictable outcomes. This is the key reason entanglement does not violate causality. Nothing you do to one particle can be used to control the outcome of the other in a meaningful way. You cannot choose the result you obtain. You can only choose what kind of measurement you perform. The universe responds with outcomes that respect the shared state, but it does not allow those outcomes to be steered into a signal. Still, the feeling of something instantaneous remains, and it is worth sitting with that feeling carefully rather than dismissing it. The discomfort often comes from trying to force quantum events into classical categories. We want to ask which particle influenced the other, and how fast that influence traveled. But entanglement suggests that this is the wrong question. There is no sequence of cause and effect connecting the outcomes. There is only a single cause, the shared state created by the earlier interaction. Measurement reveals different aspects of that state at different locations, but the source of the correlation lies in the past, not in the moment of measurement. Seen this way, the instant correlation becomes less mysterious. It is not that the universe is sending signals faster than light. It is that the universe allows physical descriptions that are not built from independent parts. When such a description is refined by measurement, the refinement applies wherever that description applies. This realization marks a turning point in understanding entanglement. The puzzle is no longer how information travels, but why the quantum world allows such shared descriptions at all. Why should reality permit states that cannot be broken into localized pieces? This question troubled many physicists deeply, including those who helped create quantum theory in the first place. Among them was Albert Einstein, who found the implications of entanglement so unsettling that he questioned whether quantum mechanics could be a complete description of reality. That unease, and the careful reasoning it inspired, is where the story naturally moves next. As unsettling as instant correlation may feel, the next piece of understanding brings a surprising sense of calm. Despite appearances, entanglement does not allow information to be sent faster than light. Nothing useful, controllable, or message-like travels between the particles when one of them is measured. This becomes clear only when we separate two ideas that are easy to blur together. Correlation is not the same thing as communication. Correlation is a pattern that becomes visible when results are compared. Communication requires control, intention, and the ability to choose what is sent. When an observer measures one particle in an entangled pair, the outcome they see is fundamentally random. They cannot decide whether the result will be one value or the other. They can choose what kind of measurement to perform, but not the result it produces. This lack of control is not a limitation of technology or technique. It is built into the structure of quantum theory itself. Because the outcome is random, it cannot be used to encode a message. A message requires choice. It requires the ability to select one outcome rather than another in order to represent information. In entanglement experiments, nature does not offer that freedom. It responds with outcomes that obey the rules of the shared state, but those outcomes arrive without regard to anyone's wishes. On the other side of the experiment, the distant observer sees nothing unusual at all. Their measurements produce a random sequence of results, indistinguishable from what they would see if the particles were not entangled. There is no sudden change, no detectable signal, no local evidence that anything has happened elsewhere. Only later, when the two observers compare notes using ordinary communication, does the pattern emerge. They line up their results and discover correlations that could not have arisen by chance. But this comparison requires time. It requires signals that travel no faster than light. Until that comparison happens, each observer's data looks ordinary and uninformative. A helpful analogy here is to imagine two people flipping coins that were prepared together in a special way. Each person flips their coin in isolation and writes down the result. Each sees a random mix of heads and tails. Nothing about their individual record reveals anything special. Only when they later place their lists side by side do they notice that the results are perfectly correlated. The correlation was real all along, but it was not usable until the records were brought together. In quantum entanglement, the situation is even stricter. The randomness is not just apparent, it is fundamental. There is no hidden pattern that could be exploited with better knowledge. This is why entanglement preserves causality so cleanly. It allows nature to be deeply connected without allowing influence to outrun light. This distinction resolves a tension that often arises when people first encounter entanglement. The word instant invites the idea of speed. It makes us imagine something traveling very fast, but nothing travels at all. The correlations are not events moving through space. They are features of a shared description that becomes visible only under specific conditions. Another way to see this is to focus on what changes when a measurement is made. Locally, something definite happens. A detector clicks. A number is recorded. But nothing changes in the statistics available to the distant observer. Their local reality remains exactly as it was before. From their perspective alone, the universe gives no hint that an entangled partner has been measured elsewhere. This is why physicists say entanglement is non-local but not non-causal. It involves relationships that span distance, but it does not allow cause and effect to violate the structure of space-time. The universe seems to permit deep correlations while still enforcing strict limits on influence. This balance is not accidental. It is one of the most carefully tested aspects of quantum theory. Experiments have been designed to push this boundary as hard as possible. Measurements are made at space-like separations, so that no signal traveling at or below the speed of light could connect them in time. Random choices of measurement settings are made at the last possible moment. Yet the results always fall into the same pattern. Strong correlations appear. No signals are found. The more these experiments are refined, the clearer the lesson becomes. Nature does not need faster than light communication to coordinate outcomes. The coordination is already present, encoded in the structure of the shared state created earlier. Understanding this removes one layer of mystery, but it sharpens another. If no information is transmitted at measurement and no hidden signals are exchanged, then how should we think about the reality of the properties being measured? Were they there all along, waiting to be revealed, or do they come into existence only when measured? This question strikes at the heart of what it means for a physical theory to be complete. If particles do not carry definite properties prior to measurement, then quantum mechanics is telling us something deeply counterintuitive about reality. If they do carry such properties, then quantum mechanics might be missing something. This tension was impossible for early pioneers of physics to ignore. It did not feel like a technical detail. It felt like a philosophical fault line running through the foundations of science. And no one was more troubled by it than Albert Einstein. Einstein accepted the empirical success of quantum mechanics, but he doubted that it was the final word. He believed that a complete physical theory should describe an objective reality, one in which physical properties exist whether or not they are observed. Entanglement seemed to threaten that picture by tying the properties of distant particles together in a way that defied classical intuition. To Einstein, the idea that measuring one particle could immediately constrain the properties of another, distant particle suggested that quantum mechanics was incomplete. He famously referred to this as spooky action at a distance, not as an endorsement, but as a warning. That discomfort would soon be sharpened into a precise argument, one that aimed to show that quantum mechanics must be missing hidden elements of reality. This argument did not rely on vague unease. It relied on logic, locality, and a deep commitment to the idea that physical properties should not depend on distant choices. Following that argument leads us directly into one of the most important debates in the history of physics, a debate that would eventually transform entanglement from a philosophical puzzle into one of the most rigorously tested features of the natural world. Einstein's unease with entanglement did not come from confusion. It came from clarity. He understood quantum mechanics deeply, and precisely because of that, he worried about what it seemed to imply about reality itself. For Einstein, physics was not just a tool for predicting outcomes. It was a way of describing a world that exists independently of observation. In that world, objects have properties whether or not anyone is looking. A planet has a position. A particle has a momentum. Measurement, in this view, reveals what is already there. It does not create it. Entanglement strained this picture. If two distant particles share a quantum state, and if measuring one immediately constrains what can be measured about the other, then something strange appears to be happening. Either the measurement on one particle is influencing the other instantly, or the particles did not have definite properties to begin with. Einstein found both options deeply troubling. Instant influence across distance seemed to violate the spirit of relativity, which he had worked so hard to establish. But the alternative, that physical properties do not exist until measured, felt like an abandonment of objective reality. Rather than dismissing the problem, Einstein approached it carefully. In 1935, together with Boris Podolsky and Nathan Rosen, he formulated what is now known as the EPR argument. It was not an attack on quantum mechanics as a predictive tool. It was a logical examination of whether quantum mechanics could be considered complete. The argument begins with a simple premise. If it is possible to predict the outcome of a measurement with certainty, without disturbing the system, then that outcome must correspond to an element of reality. This premise sounds almost obvious. If you can know something for sure without touching it, then that something must already exist. Now, consider an entangled pair of particles created together and then separated by a large distance. According to quantum mechanics, their properties are correlated. If you measure the position of one particle, you can instantly predict the position of the other. If instead you choose to measure the momentum of the first particle, you can instantly predict the momentum of the second. Crucially, the choice of what to measure can be made at the last moment. The distant particle cannot know in advance whether position or momentum will be measured on its partner. Yet, in either case, the prediction comes out perfectly. From Einstein's perspective, this leads to a stark conclusion. The distant particle must possess both a definite position and a definite momentum before any measurement is made. Otherwise, how could the correct prediction be possible? But quantum mechanics explicitly forbids this. It says that position and momentum cannot both be well defined at the same time. This creates a contradiction. Either quantum mechanics is incomplete, missing hidden elements of reality that specify these properties, or reality itself does not have definite properties independent of measurement. Einstein and his collaborators chose the first option. They argued that quantum mechanics must be incomplete. There must be additional variables, hidden from the theory, that carry the information needed to restore a classical sense of realism and locality. What makes the EPR argument powerful is that it does not rely on emotion or metaphor. It is a clean, logical construction built from assumptions that were widely accepted at the time. Locality, the idea that objects are influenced only by their immediate surroundings. Realism, the idea that physical properties exist whether or not they are observed. And completeness, the idea that a physical theory should account for all elements of reality. EPR showed that these assumptions cannot all coexist peacefully with the predictions of quantum mechanics. Something has to give. For many years, this tension remained unresolved. Quantum mechanics continued to succeed spectacularly in experiments, while debates about its meaning remained largely philosophical. Some physicists were content to treat the theory as a calculation tool and avoid deeper questions. Others proposed interpretations that softened the implications by redefining measurement or reality itself. But Einstein was not satisfied with reinterpretation. He wanted a clear answer. Either quantum mechanics was missing something, or the universe was far stranger than anyone had expected. What is remarkable in hindsight is how restrained Einstein's position was. He did not claim to know the answer. He only insisted that the question mattered, and that it could, in principle, be settled by careful reasoning and experiment. For decades, it seemed impossible to do so. The hidden variables Einstein imagined appeared inaccessible. The correlations predicted by quantum mechanics seemed to occur at distances and timescales that defied direct causal explanation. But no experiment could distinguish between quantum mechanics and a cleverly constructed hidden variable theory. The debate hovered in an uneasy state. Quantum mechanics worked. The discomfort lingered. Then, in the 1960s, a quiet conceptual breakthrough occurred. A physicist named John Bell realized that Einstein's intuition about hidden variables could be tested, not by probing the hidden variables themselves, but by examining the statistical patterns they would have to produce. Bell asked a subtle but decisive question. If the world obeys locality and realism in the way Einstein envisioned, then even with hidden variables, there should be strict limits on how strong correlations between distant measurements can be. These limits do not depend on the details of the hidden variables. They follow from the assumptions alone. Quantum mechanics, however, predicts correlations that exceed those limits. Bell's insight transformed a philosophical dispute into an experimental one. For the first time, it became possible to ask nature directly which picture it preferred. This moment marks a profound shift in the story of entanglement. The question was no longer whether quantum mechanics felt acceptable, but whether reality itself respected the constraints Einstein believed were necessary. The stage was set for experiments that would do more than confirm quantum predictions. They would force a choice between deeply held intuitions about how the universe ought to behave. And when those experiments were finally performed, with increasing care and precision, the answers they gave would be unmistakable. That is where the story turns next, into Bell's inequalities and the quiet but decisive verdict they delivered. John Bell approached the problem with unusual patience. He did not try to fix quantum mechanics, and he did not try to defend it. Instead, he asked a careful, almost modest question. If Einstein was right, and if the world really did obey locality and realism through hidden variables, then what exactly would that world be allowed to do? Bell realized that any theory built on those assumptions, no matter how clever or complex, would have to obey certain statistical limits. These limits would show up not in individual measurements, which are always noisy and unpredictable, but in large collections of results compared across distance. The details of the hidden variables would not matter. The assumptions alone would impose constraints. This was the key shift. Bell did not ask what hidden variables were. He asked what they could not do. Imagine two distant observers performing measurements on pairs of entangled particles. Each observer can choose between different measurement settings, such as different orientations of a detector. The choices are made independently, and the results are recorded as simple outcomes, often described as plus or minus, yes or no. If the particles carry hidden instructions that determine how they will respond to any possible measurement, and if no influence can travel faster than light between them, then the correlations between outcomes must obey certain inequalities. These inequalities are mathematical expressions of common-sense assumptions about locality and realism. Bell derived these inequalities with remarkable clarity. They do not rely on quantum mechanics. They do not assume anything about wave functions or collapse. They apply to any theory in which measurement outcomes are determined by pre-existing properties and no faster-than-light influence. Quantum mechanics, however, predicts correlations that violate these inequalities. Not slightly, but decisively. The predictions are precise, and they differ clearly from what any local hidden variable theory can produce. This meant that experiments could finally decide the issue. If nature obeyed Bell's inequalities, then Einstein's vision of a local, realistic world could still be viable, even if quantum mechanics needed revision. If nature violated them, then no local hidden variable theory could describe reality. What makes Bell's result so powerful is its generality. It does not depend on how clever the hidden variables are. It does not matter whether they are deterministic or probabilistic, simple or elaborate. If they respect locality, they must obey the inequalities. At first, this insight did not receive widespread attention. Bell himself was surprised by how long it took for the physics community to recognize its importance. But gradually, experimentalists began to see that the question was no longer philosophical. It was empirical. Early experiments in the 1970s and 1980s began to test Bell's inequalities using entangled photons. The setups were challenging. Detectors were imperfect. Distances were limited. There were loopholes that critics could point to, such as the possibility that measurement choices were not truly independent, or that undetected particles biased the results. Even so, the trend was clear. Again and again, experiments produced correlations that violated Bell's inequalities and matched the predictions of quantum mechanics. As techniques improved, the experiments became more refined. Detectors became more efficient. Measurement settings were changed more rapidly and randomly. Distances increased, ensuring that no signal traveling at or below the speed of light could coordinate the outcomes. In these experiments, the violations of Bell's inequalities were not marginal. They were robust. The statistical patterns were unmistakable. The universe was not behaving like a local hidden variable machine. One of the most striking aspects of these results is how quiet they are. There is no dramatic event when an inequality is violated. There is no visible signal or burst of energy. The verdict emerges slowly, from careful accumulation of data, from correlations that refuse to stay within classical limits. What Bell's work showed is that the discomfort Einstein felt was not misplaced, but it was resolved in an unexpected way. The universe does not restore classical realism by hiding variables behind the scenes. Instead, it abandons locality in a very specific, constrained manner. This does not mean that everything influences everything else instantly. It means that the structure of reality allows correlations that cannot be explained by local causes alone. The world is not built from independent pieces whose properties are fixed in advance. Some aspects of reality are genuinely relational. This conclusion is subtle, and it is often misunderstood. Bell's theorem does not say that faster-than-light signals exist. It does not say that relativity is wrong. It says that at least one of the assumptions we bring from classical thinking must be released. Different interpretations of quantum mechanics let go of different assumptions. Some give up realism, accepting that properties do not exist until measured. Others give up strict locality, allowing influences that are not mediated through space in the usual way. Still, others reinterpret what measurement means, or how probabilities should be understood. What all viable interpretations share is this: they reproduce the violation of Bell's inequalities. None of them restore the comfortable picture Einstein hoped for without paying a price elsewhere. There is something quietly profound about this. The universe was asked a very specific question, framed with care and respect for both logic and experiment. And the universe answered, consistently and without ambiguity. It did not answer with words or explanations. It answered with numbers, with patterns, with correlations that refused to fit into a classical mold. Bell himself was cautious about how to interpret this answer. He did not claim to know what reality ultimately is. He only insisted on taking the experimental results seriously, even when they challenge our deepest intuitions. In doing so, he shifted the conversation about entanglement. It was no longer a paradox to be tolerated or ignored. It was a feature of the world that demanded explanation on its own terms. Entanglement was no longer something that might go away with a better theory. It was something any future theory would have to account for explicitly. This realization changed how physicists thought about quantum theory. It encouraged a new generation of experiments, not just to test foundations, but to use entanglement as a resource. If the universe allows such strong correlations, perhaps they can be harnessed. But before that practical turn could fully unfold, one more step was needed. The experimental confirmation of Bell's predictions had to become airtight, closing every remaining loophole, leaving no room for doubt. That effort would take decades, and it would push experimental physics to its limits. But with each improvement, the same answer returned. Nature violates Bell's inequalities, and in doing so, it tells us calmly and consistently that separateness is not as fundamental as it once seemed. The implications of this realization do not arrive all at once. They unfold gradually as the experiments become more precise and the confidence grows. And as that confidence grows, entanglement shifts from being a challenge to understanding reality to being a stable, reliable feature of it. That shift opens the door to the next stage of the story, where entanglement is no longer just tested, but trusted, where it becomes something that can be engineered, manipulated, and explored in its own right. To see how deeply this trust now runs, and how thoroughly entanglement has been confirmed in the real world, we move next into the experiments themselves, and the careful ways physicists have learned to let nature speak for itself. By the hour, time experiments turned toward fully testing Bell's insight. Entanglement had moved from a thought experiment into a physical phenomenon that could be handled with care, patience, and precision. The question was no longer whether quantum mechanics made strange predictions, but whether nature would continue to honor them under the strictest possible conditions. Early experiments were already suggestive, but physicists are trained to be cautious. A result is only as strong as the assumptions it does not rely on. So, experimentalists began identifying every possible way classical explanations might still sneak through. Every loophole that could preserve Einstein's hope for a local, realistic world. One such loophole involved detection. In early photon experiments, not every particle sent toward a detector was actually registered. If the detected particles were somehow a biased subset, then perhaps the observed correlations were misleading. To address this, physicists worked to improve detector efficiency until nearly every particle was counted. When the experiments were repeated under these conditions, the violations of Bell's inequalities remained. Another loophole involved timing and communication. If the choice of measurement setting on one side somehow influenced the other side through an unnoticed signal, then the correlations could still be explained classically. To eliminate this possibility, experiments were designed so that measurement choices were made randomly and extremely quickly, after the particles were already in flight. In some setups, random number generators based on quantum processes or even distant astronomical sources were used to decide measurement settings. The idea was simple but powerful. If the choices are truly unpredictable and made too late for any signal to coordinate them, then any observed correlation must come from the shared quantum state alone. Distances increased as well. Detectors were placed kilometers apart, then tens of kilometers apart. Measurements were arranged so that, according to relativity, no signal traveling at or below the speed of light could connect the events in time. Each measurement occurred in its own space-time region, causally disconnected from the other. Again and again, the results were the same. The correlations violated Bell's inequalities exactly as quantum mechanics predicted. By the 2010s, a new generation of experiments emerged that closed multiple loopholes simultaneously. These so-called loophole-free Bell tests combined high-efficiency detectors, fast and random measurement choices, and large spatial separations. They were technically demanding and conceptually clean. When the data from these experiments were analyzed, the conclusion was unavoidable. Nature violates Bell's inequalities. No local hidden variable theory can account for the observed correlations. What is striking is how unremarkable the measurements themselves appear. There is no dramatic moment where reality seems to tear. Detectors simply click, numbers accumulate, graphs are drawn, and within those quiet patterns, a profound statement about the structure of the universe is encoded. Entanglement is not an artifact of experimental error. It is not a temporary illusion caused by imperfect instruments. It is a stable, repeatable feature of the natural world. This stability is part of what allows entanglement to feel calm once it is understood. The universe is not behaving erratically or inconsistently. It is following rules that are subtle but reliable. Once those rules are learned, they can be trusted. Experimental confirmation also revealed something else. Entanglement is not limited to tiny, fragile systems observed only under ideal conditions. It can be created between particles separated by large distances. It can persist long enough to be manipulated. It can survive transport through optical fibers, through open air, even through space. Satellites have distributed entangled photons between ground stations separated by hundreds of kilometers. Atomic systems have been entangled across laboratory rooms. Superconducting circuits have shared quantum states across engineered devices. Each of these achievements rests on the same foundational understanding confirmed by Bell tests. What this tells us is that entanglement is not a delicate exception. It is a robust aspect of quantum reality. There is a quiet humility in how these experiments are conducted. Physicists do not ask nature to explain itself. They ask it to behave consistently. They set up conditions, remove alternatives, and listen carefully to the data. And nature responds in the same way every time. This consistency reshaped how entanglement is viewed. It is no longer a puzzle hovering at the edge of theory. It is a working principle, something that can be quantified, measured, and used. At the same time, the experiments do not tell us why entanglement exists. They do not resolve the deeper, interpretive questions about what the quantum state represents or how measurement should be understood. Those questions remain open, explored through different interpretations of quantum mechanics. But the experiments do something just as important. They tell us which paths are no longer available. They tell us that the universe does not operate according to local realism in the classical sense. Whatever the underlying picture turns out to be, it must accommodate non-local correlations as a fundamental feature. This realization has a gentle but profound effect on how we think about physical explanation. It suggests that the universe is not built solely from independent pieces interacting locally. Some aspects of reality are encoded in relationships that cannot be decomposed into parts without loss. Seen this way, entanglement feels less like a violation and more like an expansion. It expands the kinds of structures physics is allowed to describe. It invites us to think in terms of wholes as well as parts, of global constraints as well as local events. The experimental confirmation of entanglement also marked a cultural shift within physics. Foundational questions, once seen as philosophical distractions, became central again. Precision experiments could now probe the deepest assumptions about reality, and they did so with remarkable clarity. As confidence in entanglement grew, a new attitude emerged. Instead of asking whether entanglement is real, physicists began asking how it can be characterized, preserved, and controlled. How strong is it? How long does it last? How does it degrade? How can it be shared among many systems? These questions are not driven by mystery alone. They are driven by the recognition that entanglement behaves like a physical resource. It can be created, consumed, transformed, and lost. It obeys rules, and those rules can be studied. This marks another turning point in the story. Entanglement transitions from being something that challenges our intuition to something that can be harnessed, from something that unsettles to something that enables. But before exploring what entanglement can do, it is worth pausing on what it has already taught us. The experiments have shown that reality is consistent, but not classical. That locality, as once imagined, is not absolute, and that the universe is willing to support correlations that transcend spatial separation without allowing causality to break. These lessons do not arrive with drama. They arrive with patience, with repeated trials, with careful elimination of alternatives, and once they arrive, they remain. From this stable foundation, new possibilities open naturally. If entanglement is real, robust, and measurable, then it is something physics can work with rather than work around. This realization leads directly to the next stage, where entanglement is treated not as a paradox to be explained away, but as a feature to be understood on its own terms. A feature that reshapes how we think about information, connection, and the structure of physical law. That step brings us to the idea of non-locality itself, not as a signal or force, but as a property of nature that must be carefully defined, limited, and respected. And it is there, in that refined understanding, that entanglement begins to reveal its quiet coherence. With entanglement now firmly established by experiment, the word non-locality inevitably enters the conversation. It is a word that can sound dramatic, even unsettling, but its meaning in physics is far more precise and restrained than it first appears. Non-locality does not mean that objects are constantly influencing each other across space. It does not mean that causes leap instantly from one place to another. And it does not mean that space itself has become irrelevant. What it means is something quieter and more specific. It means that the outcomes of certain measurements cannot be fully explained by properties that are confined to individual locations. In classical physics, locality is a deeply ingrained idea. Objects are influenced by what touches them, or by forces that propagate through space over time. If two events are far apart, then any connection between them must be carried by something moving between them. This picture works extraordinarily well for everyday phenomena, and even for much of modern physics. Quantum entanglement does not overthrow this picture entirely. Instead, it reveals its limits. When physicists say that entanglement is non-local, they are pointing to the fact that the correlations observed between distant measurements cannot be reduced to independent local causes. The explanation for the correlation does not live entirely at either measurement site. It lives in the shared quantum state that spans both. This is an important distinction. The non-locality of entanglement is not something that happens at the moment of measurement. It is something that exists beforehand, encoded in the structure of the state created by interaction. Measurement reveals this structure. It does not generate it. A useful way to think about this is to imagine a carefully stretched fabric. If you press down on one part of the fabric, the pattern of tension across the entire surface determines how the fabric responds. The response at a distant point is not caused by a signal racing across the fabric at the moment you press. It is determined by the global structure of the fabric itself. The press reveals that structure rather than transmitting information through it. In entanglement, the quantum state plays the role of that global structure. It is not located at a point. It is a description that applies to the system as a whole. When a measurement occurs, the outcome is constrained by that description everywhere it applies. This perspective helps clarify why non-locality does not conflict with relativity. Relativity places limits on how influences propagate through space-time. It does not forbid global constraints on physical systems. Entanglement operates through constraints, not signals. Different observers, moving at different speeds, may disagree about the order in which measurements occurred. One observer may say that the measurement on the left happened first. Another may say the measurement on the right happened first. Quantum mechanics accommodates all of these perspectives without contradiction, because the theory does not assign a causal sequence between the outcomes. The correlations do not depend on which measurement came first. They depend only on the shared state and the measurement choices. This symmetry is one of the reasons entanglement fits so naturally within relativistic spacetime, despite its non-local character. Non-locality also does not mean that everything is connected to everything else in an unrestricted way. Entanglement has structure. It can be strong or weak. It can be shared between certain systems and not others. It can be degraded by interaction with the environment. It obeys precise mathematical rules that limit how it can be distributed. For example, entanglement cannot be freely copied or amplified. This is not a technological limitation, it is a fundamental property. If two particles are maximally entangled with each other, they cannot be equally entangled with a third particle. Entanglement is exclusive in a way that classical correlations are not. This exclusivity reinforces the idea that entanglement is not a loose, mystical connection. It is a specific, quantifiable relationship governed by strict constraints. Non-locality, in this sense, is disciplined. Understanding non-locality as a property of quantum states rather than as a mechanism of influence allows the discomfort to soften. The universe is not behaving recklessly. It is behaving consistently, but according to rules that are broader than classical intuition anticipated. This shift in perspective also changes how explanation itself is understood. In classical thinking, to explain a correlation is to trace a chain of causes through space and time. In the quantum world, explanation sometimes takes a different form. It involves identifying the global constraints that limit what outcomes are possible, even when events are separated. This does not mean that causality disappears. Local actions still have local consequences. You choose a measurement setting here, and that choice affects what can be observed here. What changes is that the full explanation of the pattern cannot be localized to any single place. There is a quiet elegance in this. The universe appears to balance locality and non-locality with care. It allows global structure without global control. It allows correlations without communication. It allows connection without collapse of causality. Once non-locality is understood in this way, it no longer feels like an anomaly that needs to be explained away. It feels like a natural extension of the idea that physical laws can apply to systems as wholes, not just to their parts. This understanding has practical consequences. It guides how physicists think about isolating systems, about protecting entanglement from the environment, about designing experiments that preserve or reveal these global properties. It informs the language used to describe quantum processes, shifting emphasis from objects to relationships. And slowly, almost quietly, it changes intuition. The world begins to feel less like a collection of independent pieces and more like a network of constraints and possibilities, shaped by interaction and history. At this stage, entanglement has fully emerged from paradox into principle. It is no longer something that threatens the coherence of physics. It enriches it. But the story does not end with understanding alone. Once physicists recognized that entanglement is real, robust, and governed by clear rules, a natural question followed. If entanglement is a genuine feature of the world, can it be treated as something physical, something that can be used, managed, and transformed? This question does not diminish the conceptual depth of entanglement. It builds on it. It asks how this subtle form of connection fits into the broader economy of physical resources. Answering that question leads into the idea of entanglement as a resource, something that can be spent, conserved, and traded in carefully defined ways. And that shift from understanding what entanglement is to understanding what it can do opens a new and surprisingly practical chapter in the story. Once entanglement is understood as real, stable, and governed by clear rules, it begins to take on a new character. It stops being only something to interpret and becomes something to work with. Physicists start to treat entanglement not as a philosophical curiosity, but as a physical resource, something that can be created, preserved, consumed, and transformed. In classical physics, resources are familiar. Energy can be stored, transferred, or dissipated. Information can be copied, erased, or transmitted. These resources obey accounting rules. You can track where they go and how much remains. Entanglement, surprisingly, fits into this same framework, even though it does not resemble any classical quantity. To see how this works, it helps to notice that entanglement is not all or nothing. Two systems can be weakly entangled or strongly entangled. They can share a small amount of correlation or a maximal amount. Physicists can quantify this using precise measures that behave consistently across different situations. What makes entanglement resource-like is that it enables tasks that would otherwise be impossible. Certain quantum operations cannot be performed at all unless entanglement is available, and once it is used, it is typically consumed, no longer present in its original form. One of the clearest examples is quantum teleportation. Despite its dramatic name, quantum teleportation does not involve transporting matter or energy from one place to another. It involves transferring a quantum state, and it cannot happen without entanglement. In teleportation, two distant parties share an entangled pair prepared in advance. When one party performs a specific joint measurement involving their half of the entangled pair and the system whose state is to be transferred, the original state is destroyed locally. With the help of a small amount of ordinary communication, the distant party can then reconstruct that state on their own system. What makes this remarkable is that the quantum state itself never travels through space. It is neither copied nor sent as a signal. The ability to reconstruct it relies entirely on the shared entanglement. Once the process is complete, that entanglement is gone. It has been spent. This spending behavior is what marks entanglement as a resource. You cannot use the same entangled pair to teleport again. You must create fresh entanglement for each transfer. The universe enforces this bookkeeping strictly. Another example appears in quantum cryptography. Certain cryptographic protocols use entangled particles to generate shared secret keys between distant parties. The security of these protocols does not rest on computational difficulty, as it does in classical cryptography. It rests on the structure of quantum correlations. If an eavesdropper tries to intercept or measure the entangled particles, the correlations change in detectable ways. Entanglement makes intrusion visible. Again, this capability exists only because of the specific non-classical correlations entanglement provides. Here too, entanglement behaves like a consumable resource. Using it to generate a key degrades it. Once measured, it cannot be reused in the same way. Physicists also discovered that entanglement obeys conservation-like rules. You cannot create entanglement out of nothing using only local operations and classical communication. You must invest interaction, coherence, or prior entanglement. This mirrors the way energy cannot be created without input. At the same time, entanglement can be transformed. Weak entanglement can sometimes be concentrated into stronger entanglement through carefully designed protocols, at the cost of discarding some systems. Strong entanglement can be diluted to spread correlations across many systems. These transformations resemble refining and distributing resources rather than creating them anew. This perspective leads to a striking realization. Entanglement is not just a feature of quantum systems. It is a currency of quantum information. It determines what is possible and what is not when manipulating quantum states across space. Seeing entanglement this way has a calming effect on its interpretation. Instead of asking endlessly what entanglement means, physicists can ask what it does, and the answers are precise, testable, and reliable. Importantly, treating entanglement as a resource does not require resolving every interpretive question about quantum mechanics. Different interpretations agree on how entanglement behaves operationally. They may disagree on what the quantum state represents, but they agree on how entanglement can be used and how it cannot. This agreement gives entanglement a solid footing in physics. It becomes part of the working toolkit, not an unresolved anomaly. There is something quietly reassuring about this. The universe allows deep, non-local correlations, but it also constrains them. It does not allow unlimited sharing. It does not allow copying. It does not allow control beyond specific limits. Entanglement expands what is possible without dissolving structure. As experiments become more sophisticated, physicists learn how to protect entanglement from decoherence, how to distribute it over long distances, how to store it temporarily, and how to verify its presence. Each of these tasks requires careful attention to the same principles that define entanglement in the first place. The environment remains a constant challenge. Any uncontrolled interaction tends to spread entanglement outward, diluting it among many degrees of freedom. This is why maintaining entanglement requires isolation, cooling, and precise timing. But the challenge itself reinforces the resource picture. Something that can be lost, degraded, and preserved behaves like something physical. This resource-based view also reframes earlier philosophical concerns. The question of whether entanglement is strange becomes less urgent than the question of how it behaves. And its behavior is remarkably consistent. Entanglement does not allow paradoxical actions. It does not enable faster than light communication. It does not permit contradictions. It allows exactly what it allows, no more and no less. In this sense, entanglement feels less like a disruption of physics and more like an extension of it. Classical physics described what could happen when systems were independent. Quantum physics describes what can happen when systems are fundamentally linked. The two pictures are not in conflict. They apply at different scales and under different conditions. Entanglement fades naturally in large, warm, noisy systems, which is why the classical world feels local and separable. At small scales where isolation is possible, the deeper structure becomes visible. Understanding entanglement as a resource also brings a subtle shift in how we think about separateness itself. Separation is no longer the default state of nature. It is a special condition achieved through interaction with the environment. Left alone, quantum systems tend to become entangled with whatever they encounter. This does not mean that everything is entangled with everything else in a way that matters. Most entanglement is diffuse and inaccessible. But it does mean that connection, not isolation, is the underlying tendency. There's no need to romanticize this. It is simply how the mathematics and experiments align. Entanglement is the rule, not the exception. Classical separability is the emergent simplification. Once this is accepted, the final reflections of the topic come into focus naturally. Entanglement no longer feels like a challenge to understanding. It feels like a reminder that understanding itself sometimes requires letting go of assumptions that once felt unquestionable. Physics has always progressed this way. It does not discard intuition lightly. It refines it. It stretches it until it can accommodate new evidence without breaking. Entanglement stretches intuition about individuality, distance, and independence. But it does so gently through consistent rules and repeatable outcomes. What remains, after all the experiments, arguments, and applications, is not a sense of chaos, but of quiet coherence. The universe allows relationships that are deeper than spatial separation, while still preserving order, causality, and structure. And in that balance, entanglement finds its place, not as a mystery to be feared, but as a feature to be understood, respected, and, when handled carefully, used. The final implications of this understanding do not arrive as a conclusion. They arrive as a softened view of what it means for things to be connected at all. Once entanglement is understood as a reliable physical resource, it begins to quietly shape the direction of modern physics and engineering. Not by spectacle, and not by promises of magic, but by offering new ways to perform tasks that are otherwise impossible within classical limits. One of the clearest places this appears is in quantum computing. A classical computer stores information in bits that are either 0 or 1. A quantum computer stores information in quantum bits, or qubits, which can exist in combinations of states. But it is entanglement that allows collections of qubits to behave as something more than a set of independent parts. When qubits are entangled, the information they carry is no longer localized. The state of the system is encoded across the whole collection. Operations performed on one part of the system affect the structure of the whole, not by transmitting signals, but by reshaping the shared quantum state. This allows certain computations to explore many possibilities at once in a structured way. The speed-up does not come from trying every answer blindly. It comes from interference, from amplifying correct paths and suppressing incorrect ones through carefully designed operations that rely on entanglement to coordinate the behavior of qubits. Importantly, entanglement alone does not make a quantum computer powerful. It is a necessary ingredient, but not a sufficient one. The system must also be precisely controlled, shielded from the environment, and guided through specific sequences of operations. But without entanglement, the advantage disappears. The computation collapses back into something that can be efficiently simulated classically. This reveals something subtle. Entanglement is not useful because it is strange. It is useful because it creates structure. It allows information to be distributed in ways that classical systems cannot replicate. A similar story unfolds in quantum communication. In classical communication, information is sent by encoding it into physical signals that travel through space. In quantum communication, entanglement allows information-related tasks to be accomplished without sending the information itself in the usual sense. Quantum teleportation is one example, but there are others. Entanglement can be used to synchronize distant systems, to verify identity, and to establish shared references with security guaranteed by the laws of physics rather than by assumptions about computational power. In quantum key distribution, entanglement ensures that any attempt to intercept the communication leaves a detectable trace. This does not rely on secrecy of algorithms or difficulty of mathematical problems. It relies on the fact that entanglement cannot be accessed without disturbance. The structure of quantum correlations itself enforces honesty. Here again, entanglement behaves like a constrained resource. It enables security, but only if handled carefully. Noise, loss, and environmental interaction can degrade it. Protecting entanglement becomes a practical challenge, one that pushes the development of better materials, better isolation techniques, and better error correction strategies. Quantum sensing offers another window into entanglement's practical role. Certain measurements, such as detecting extremely weak magnetic fields or subtle changes in time and frequency, can be performed with greater precision when entangled systems are used. Entanglement allows noise to be redistributed in a way that sharpens sensitivity beyond classical limits. In these applications, entanglement does not violate uncertainty. It works with it. By correlating systems, uncertainty can be shifted from one measurement outcome to another, improving precision where it matters most. This is another example of entanglement acting not as a loophole, but as a structured reallocation of physical limits. What ties all of these technologies together is restraint. None of them exploit entanglement as a means of faster-than-light communication or control. They respect the same constraints that preserve causality. Entanglement enables coordination without transmission, security without secrecy, and precision without excess energy. This consistency reinforces the idea that entanglement fits naturally into the broader framework of physics. It does not demand exceptions. It demands careful design. As these technologies develop, they also deepen understanding. Each practical challenge reveals more about how entanglement behaves under real conditions, how it decays, how it can be refreshed, how it spreads, how it resists isolation. In this sense, technology and theory move together. Experiments designed for application also test foundational ideas. They probe how non-local correlations survive in complex systems, how they scale, and how they interact with classical control mechanisms. There is something quietly circular about this progress. Entanglement began as a theoretical curiosity, then became a philosophical challenge, then an experimental fact, then a resource, and now a tool. Each stage reinforces the previous one without exhausting it. Yet, even as entanglement becomes more familiar in laboratories and devices, it does not lose its conceptual depth. Using entanglement does not require fully explaining why it exists. Physics often works this way. Gravity was used long before it was deeply understood. Electricity powered technology before its microscopic nature was known. Understanding and use grow together, each informing the other without demanding completion. As entanglement becomes embedded in technology, it also reshapes education. Students learn not only how to calculate entanglement, but how to think in terms of shared states and relational properties. The mental shift that once felt radical becomes part of ordinary training. And gradually, almost imperceptibly, intuition adapts. What once felt like a violation of common sense becomes a new form of sense. Not because the universe has changed, but because the mind has learned to accommodate a wider set of possibilities. At this point in the story, entanglement has been explored from every necessary angle. Its creation, its measurement, its limits, its experimental confirmation, its non-local structure, and its practical use have all been examined carefully and calmly. There is no remaining paradox that demands resolution before moving forward. There is only the open question of interpretation, of what this structure suggests about the nature of reality itself. And that question does not require urgency. It does not demand a final answer. It invites reflection grounded in what has already been established. The science has done its work. The universe has spoken through experiment. What remains is to notice what kind of picture this leaves us with. Not a dramatic one, not a mystical one, but a quietly altered one. That reflection forms the final movement of this exploration, not as a conclusion, but as a gentle widening of the perspective, shaped entirely by the physics already in place. When all of the physics is laid out carefully, when the experiments have spoken and the mathematics has settled, entanglement leaves behind a quiet shift in how reality itself is pictured. Not a conclusion and not a proclamation, but a subtle change in what feels natural to assume. For much of human history, separateness felt fundamental. Objects occupied places. Causes flowed locally. To understand something was to break it into parts and explain how those parts interacted. This approach worked so well that it became almost invisible, woven into intuition itself. Quantum entanglement does not overturn this way of thinking, but it reveals that it is incomplete. It shows that there are situations where the most faithful description of reality is not one object here and another object there, but a single system whose properties are shared. What is striking is how restrained this suggestion is. Entanglement does not say that everything is one in a poetic or mystical sense. It does not erase individuality or dissolve structure. Instead, it says that individuality is sometimes conditional, that under certain circumstances, the universe prefers relationships over parts. The physics does not ask us to abandon clarity. It asks us to expand it. Entangled particles still exist in space. They still interact locally with detectors. They still obey conservation laws and causal limits. Nothing about entanglement removes the physical world from the framework of space-time. What changes is where explanation lives. In classical thinking, explanation lives at points. This happened here, which caused that to happen there. In entanglement, explanation sometimes lives in the preparation of the system as a whole. The cause of the correlation lies in a shared past interaction, not in a sequence of local events unfolding afterward. This can feel unfamiliar at first, but it is not unprecedented. Even in classical physics, global constraints play a role. The shape of a bridge determines how forces distribute through it. The boundary conditions of a drum determine its vibrational modes. These are not local causes traveling through space. They are structural facts about the system. Entanglement extends this idea into the quantum domain, where the structure is not geometric but probabilistic, not visible but precisely defined. The universe allows global quantum structures that persist even as their parts move apart. Once this is accepted, a certain tension eases. The need to ask which particle influences the other begins to fade. That question belongs to a picture where particles are always independent to begin with. Entanglement shows that this independence is sometimes an approximation, not a rule. There is also a quiet humility embedded in this realization. Quantum mechanics does not tell us what reality must be like in absolute terms. It tells us what kinds of descriptions work, what kinds of explanations survive contact with experiment. Entanglement survives that contact remarkably well. Every attempt to remove it, to explain it away with hidden signals or pre-existing instructions, has failed. Every careful experiment reinforces the same lesson. The universe is willing to coordinate outcomes across distance without exchanging information, willing to encode properties in relationships rather than locations. This does not make reality unknowable. It makes it more subtle. The limits remain clear. You cannot use entanglement to control distant events. You cannot exploit it to violate causality. You cannot extract definite properties without interaction. The universe is generous with correlation, but strict with control. This balance is what gives entanglement its calmness once understood. It is not chaotic. It is not arbitrary. It is precise, constrained, and consistent. In this way, entanglement quietly reshapes what objectivity means. Objectivity does not require that every property belong to an isolated thing. It requires that descriptions be consistent, testable, and shared among observers. Entangled states meet that requirement fully. Two observers, separated by great distance, can agree on the structure of the correlations they observe. They can predict them, test them, and rely on them. The objectivity is not lost. It is relocated from individual properties to joint ones. This shift also changes how measurement is viewed. Measurement is no longer just revealing what was already there. It is participating in the realization of one outcome from a structured set of possibilities. This participation is not mystical. It is physical interaction, governed by well-defined rules. The universe does not wait passively to be observed, but it does not invent outcomes arbitrarily either. It responds within constraints that were already in place. There is something deeply stabilizing about this picture. Reality is neither fully predetermined nor fully unconstrained. It unfolds within a framework that allows novelty without chaos. Entanglement also invites a gentler view of connection. Not connection as influence, but connection as shared history. Entangled particles were once part of the same process. They carry that history with them, encoded in the structure of their joint state. In this sense, entanglement is not about distance at all. It is about origin. Distance changes where particles are. It does not erase where they came from. This idea resonates beyond physics without needing to be pushed there. It stays grounded in experiment, in equations, in detector clicks, and yet it subtly loosens the grip of certain assumptions, opening space for new intuition to form. The universe, as revealed through entanglement, is not fragmented at its deepest level. It is relational. Not everywhere, not always, but where quantum systems are allowed to remain coherent. And coherence itself becomes something to appreciate. It is fragile, easily disrupted, quickly lost in the noise of large systems. The classical world we live in is the world where coherence has mostly faded, where entanglement has been spread so thin that it no longer matters. This is why everyday experience feels local and separable. Not because the universe is fundamentally that way, but because complexity washes out the deeper structure. Knowing this does not make the world feel less solid. It makes it feel layered. There is the layer of daily experience, where objects are distinct and causes are local. And beneath it, there is a layer where description belongs to systems rather than parts, where correlations reflect shared origin rather than exchange. Both layers are real. One emerges from the other. Entanglement does not ask to replace common sense. It asks to recognize its domain of validity. As physics continues to explore this domain, it does so without urgency. There's no need to rush toward a final interpretation. The experiments are clear enough to guide understanding and open enough to allow reflection. This openness is not a failure of explanation. It is a sign of maturity. Physics has learned where its statements are sharp and where they are suggestive. Entanglement is sharp in its predictions and suggestive in its implications. It tells us exactly what correlations will appear and exactly what limits cannot be crossed. And it gently hints that separateness, while useful and often accurate, is not the deepest organizing principle nature has to offer. This hint does not demand belief. It invites familiarity. With time, what once felt strange becomes simply another way the universe behaves. Not more dramatic than gravity curving space, not more mysterious than time dilating with speed. Just another reminder that intuition evolves. And in that evolution, there is a quiet comfort. The universe does not resist understanding. It rewards patience. Entanglement, once approached calmly and followed carefully, reveals not a fracture in reality, but a deeper continuity. A continuity that allows distance without disconnection, randomness without chaos, and structure without rigidity. Nothing about this needs to be resolved tonight. It is enough to let the picture rest as it is, coherent, tested, open. The universe remains exactly where it was, doing exactly what it has always done. Only the way it is seen has softened, widened, and grown a little more precise. With the picture of entanglement now settled as a stable feature of nature, another quiet question naturally emerges. If entanglement is not about signals moving through space, and not about influence traveling faster than light, then what is it really anchored to? What gives it its persistence, its structure, its resilience across distance? The answer begins to come into focus when attention shifts from space to time. Entanglement is born at a moment. It is created when systems interact, when they participate in the same physical process. That moment leaves an imprint, not a memory in the human sense, but a physical record encoded in the joint quantum state. From that point on, the particles may separate, drift apart, even move into regions of space that can no longer communicate with each other directly. Yet the structure established by that shared past remains active. The correlations observed later are not coordinated in the present. They are inherited from the past. Seen this way, entanglement is less like a bridge stretching across space and more like a fossil imprint left by interaction. The present measurements are shaped by a history the particles once shared. This reframing softens many of the remaining intuitions that tend to resist entanglement. Nothing reaches out across the universe when a measurement occurs. Nothing reacts. Instead, a pre-existing structure is consulted, the way a melody resolves according to the key it was written in, regardless of where or when it is played. The universe is not coordinating outcomes in real time. It is respecting constraints laid down earlier. This perspective aligns naturally with relativity. Relativity tells us that simultaneity is not absolute, that different observers can disagree about the order of distant events. Entanglement fits comfortably within this framework because it does not require a universal present moment where coordination occurs. The correlations do not depend on which measurement happened first. They depend on the fact that both measurements are probing the same shared state, a state defined by a common origin. In this sense, entanglement is deeply temporal. It is about how the past limits the present, not about how the present reaches across space. This also helps explain why entanglement feels fragile. Any new interaction is another moment in time, another opportunity for the system to share its correlations with something else. Each interaction spreads the original imprint thinner, distributing it across more degrees of freedom. Decoherence, then, is not the destruction of entanglement so much as its dilution through history. The past becomes crowded with interactions, and the original clean correlations become harder to isolate. The classical world emerges from this accumulation. It is the world where systems have long, complex histories of interaction, where no single shared origin dominates the present. In that world, separateness becomes a good approximation. But at small scales, or over short histories, the imprint of shared origin remains sharp. This way of thinking also changes how measurement itself is viewed. Measurement becomes just another interaction in time, one that links a microscopic system to a macroscopic record. It does not reach backward or sideways. It simply adds another layer to the system's history. The outcome we observe is not created in isolation. It is shaped by everything that came before. There is a quiet continuity in this. The universe is not constantly improvising. It is unfolding according to constraints accumulated over time. Entanglement is one of the ways those constraints persist. From this perspective, the non-local character of entanglement feels less like a rupture and more like a reminder that space is not the only organizing principle in physics. Time, history, and interaction play equally fundamental roles. Entangled systems are not connected because they are far apart. They are connected because they were once together. Distance does not undo that fact. Only new interaction can. This understanding also sheds light on why entanglement cannot be used to send messages. You cannot change the past interaction that created the shared state. You can only choose how you interrogate it in the present. The structure you reveal is already fixed. You can ask different questions, but you cannot rewrite the answers. This places entanglement firmly within a calm, disciplined universe. The past matters. The present reveals. The future unfolds within constraints. Nothing is frantic. Nothing is instantaneous in the sense of reaction. Everything is consistent. As this view settles in, the universe begins to feel less like a stage where distant actors coordinate behind the scenes, and more like a tapestry woven gradually through interaction. Each thread crosses others at specific moments, and those crossings determine what patterns can later appear. Entanglement is one of those crossings. And, like all crossings, it gains meaning not from where the threads end up, but from the moment they met. This temporal grounding does not answer every interpretive question about quantum mechanics, but it brings a sense of orientation. It tells us where to look for explanation and where not to look. We do not need to imagine signals darting through space. We need to pay attention to shared history. This is a gentler demand. It asks for patience rather than force. And in that patience, the remaining strangeness of entanglement continues to soften. The universe, seen through this lens, is not violating intuition. It is extending it across time as well as space. What follows from this is not a new mystery, but a deeper coherence. The same principles that govern interaction, conservation, and causality also govern entanglement. They simply operate at a level where relationships matter as much as locations. This realization does not close the story. It opens it further, not by adding complexity, but by revealing continuity where separation once seemed obvious. And that continuity can be allowed to rest, just as it is, without needing to be resolved into final statements. Because the universe is not asking to be finished. It is only asking to be noticed carefully, one interaction at a time. As attention lingers on shared history and interaction, another idea begins to surface naturally, one that has quietly grown within modern physics over the last few decades. It is the suggestion that entanglement may not merely exist within space and time, but may help give rise to some aspects of their structure. This idea does not arrive suddenly, and it does not come from speculation alone. It emerges from careful attempts to reconcile quantum mechanics with gravity, two theories that are both extraordinarily successful and yet deeply different in how they describe reality. In general relativity, space and time are not passive backgrounds. They are dynamic. They bend, stretch, and respond to energy and motion. Space-time has structure, and that structure determines how objects move. In quantum mechanics, by contrast, the primary focus is on states, probabilities, and correlations. Space appears as a stage on which quantum systems are defined, but it is not itself quantized in the same way. For a long time, these perspectives resisted unification. But as physicists looked more closely at entanglement, they noticed something intriguing. The patterns of entanglement between parts of a quantum system seemed to reflect geometric relationships. In certain theoretical models, systems that are strongly entangled behave as though they are close together, even if they are not adjacent in any obvious spatial sense. Systems that share little entanglement behave as though they are far apart. Distance, in these models, is not fundamental. It emerges from how information is shared. This does not mean that physical space is an illusion. It means that the familiar geometry of space may arise from deeper quantum relationships, with entanglement acting as a kind of connective tissue. A useful way to picture this is to imagine a network made of many nodes, each representing a quantum degree of freedom. The nodes are not arranged on a grid to begin with. Instead, they are connected by links whose strength represents how entangled the nodes are with one another. As the network grows, and the pattern of entanglement becomes structured, a sense of geometry emerges. Some nodes cluster together, others remain loosely connected. The overall pattern begins to resemble a space, not because space was imposed, but because relationships created it. In this view, space-time is not the starting point, it is the result. This idea finds support in several areas of theoretical physics, particularly in studies of black holes and quantum gravity. In these contexts, entanglement plays a central role in determining how information is distributed and how spacetime regions relate to one another. Black holes, once thought to erase information, are now understood to store it in highly entangled states. The way that information is encoded and shared appears to be deeply tied to the geometry of the spacetime around the black hole. Here again, entanglement does not behave like a signal or a force. It behaves like structure. What is striking about this line of thought is how conservative it actually is. It does not discard known physics. It builds on it. It takes the experimentally confirmed reality of entanglement seriously and asks what kind of world would naturally accommodate it. The answer seems to be a world where relationships are as fundamental as locations. This does not mean that the chair you are sitting on is held together by entanglement in any practical sense. At everyday scales, entanglement is spread thin, washed out by interaction and noise. Classical geometry dominates. Space feels solid and stable. But at the deepest levels, where quantum effects remain coherent, the scaffolding of spacetime itself may be woven from correlations. If this is the case, then entanglement is not just something that happens in the universe. It is something the universe is partially made of. This idea is still under active investigation. It is not a settled conclusion, and it is approached with caution. But it reflects a broader trend in physics, a willingness to let experimentally grounded features like entanglement guide the search for deeper structure. Importantly, this approach avoids mysticism. It does not appeal to hidden dimensions or undefined forces. It stays anchored in well-tested principles and extends them carefully. Entanglement, once seen as a problem to be explained away, becomes a clue. And, like all good clues, it does not shout. It points. It points toward a picture where space is not merely an arena in which events unfold, but a pattern that emerges from how systems are allowed to relate. Time, too, becomes less like a ticking background and more like an ordering of interactions, a sequence in which correlations are established and transformed. This perspective also brings a quiet unity to earlier themes: shared history, global constraints, non-local correlations, and the emergence of classical separability all fit within a single narrative. The universe builds itself through interaction, and the traces of those interactions define what is later possible. Nothing in this picture requires urgency. These ideas are unfolding slowly through decades of work, and they will continue to evolve. What matters is not whether a final answer is reached, but that the questions are being shaped by what nature has already revealed. Entanglement has earned its place as a guide, not because it is exotic, but because it is honest. It reflects exactly what experiments show, without exaggeration and without apology. As this view settles, there is a gentle sense of orientation. The universe feels less like a collection of objects floating in space, and more like a web of relationships that gradually crystallize into the structures we recognize. This does not diminish the reality of space and time. It deepens it. And in that deepening, the story of entanglement continues, not as something to be resolved, but as something to be lived with intellectually. A feature of the world that invites patience, attentiveness, and trust in the slow alignment of theory and experiment. There is no need to reach for final meanings here. It is enough to notice that the universe, when examined carefully, prefers coherence over isolation, structure over chaos, and relationship over fragmentation. Entanglement is simply one of the ways that preference becomes visible. And, as with all such visibility in physics, it arrives not with force, but with clarity. The clarity can be allowed to rest, doing nothing more than what it already does, holding the universe together, quietly, through the relationships it permits to exist. As the idea of entanglement shaping structure settles, one more question naturally follows, one that touches daily experience without ever announcing itself. If entanglement is so fundamental, so widespread at the quantum level, then why does the world around us feel so stable, so local, so solid and separate? The answer does not come from denying entanglement, but from understanding what happens to it. At the smallest scales, quantum systems are delicate. They maintain coherence only when interactions are limited and controlled. But the world we inhabit is full of interaction. Every object is constantly exchanging energy with its surroundings, colliding with air molecules, absorbing and emitting light, vibrating internally. Each of these interactions leaves a trace. From a quantum perspective, every interaction is an opportunity for entanglement to spread. When a small system becomes entangled with its environment, the shared quantum state grows rapidly in complexity. What was once a clean, well-defined correlation between a few degrees of freedom becomes distributed across countless others. The information that once described a simple relationship is no longer accessible in practice. This process is called decoherence, but the name matters less than the effect. Decoherence does not destroy quantum states, it disperses them. Imagine a drop of ink placed into still water. At first, the ink is localized, its structure visible and coherent. As time passes, the ink spreads, diffusing through the water until its original form is no longer distinguishable. The ink has not vanished. It has become too distributed to track. Quantum coherence behaves in much the same way. Entanglement spreads outward into the environment, linking the system to countless microscopic details. Recovering the original correlations would require reversing an astronomical number of interactions, something that is not physically possible. As a result, the system begins to behave classically. This transition does not happen because quantum rules stop applying. It happens because the quantum description becomes too large and too entangled to resolve. What remains, accessible, are stable patterns that behave as if objects have definite properties, as if they are independent, as if they follow classical cause and effect. The classical world is not a different world layered on top of the quantum one. It is what the quantum world looks like after entanglement has spread beyond retrieval. This is a deeply calming realization. It means that the solidity of everyday experience is not an illusion. It is an emergent stability. It arises naturally from the same rules that govern entanglement, not in spite of them. A chair feels solid not because quantum uncertainty disappears, but because the chair is entangled with so much of its environment that its position becomes extraordinarily well-defined. Any attempt to observe it more precisely only increases that entanglement, reinforcing its classical behavior. In this sense, classical reality is self-stabilizing. Interaction reinforces definiteness. This also explains why macroscopic superpositions are so hard to observe. To place a large object into a delicate quantum state would require isolating it from virtually all environmental interaction. Even a single stray photon can entangle the object with the outside world, dispersing coherence almost instantly. The universe is not hostile to quantum behavior, it is simply busy. Every moment is filled with interaction, and interaction carries history forward. Decoherence is the accumulation of that history. Seen this way, the arrow of time itself begins to take on a familiar shape. As entanglement spreads, information about precise quantum relationships becomes inaccessible. The future contains more entanglement than the past. This growth is not a law imposed from outside. It is a statistical tendency rooted in interaction. The past is simpler because it contains fewer interactions. The future is more complex because it contains more, This is why certain processes feel irreversible. Not because reversal is forbidden, but because reversal would require coordinating an impossibly large number of entangled degrees of freedom. The universe allows it in principle, but not in practice. Entropy, often described as disorder, is more accurately described as the spread of correlations. Entanglement is one of the ways those correlations are carried. This brings the story of entanglement full circle. What began as a puzzling connection between distant particles turns out to be the same mechanism that underwrites the stability of the everyday world. The same rules that allow deep non-local correlations also explain why tables stay put and clocks tick reliably. There is no contradiction here, only scale. At small scales, entanglement is visible and striking because coherence is preserved. At large scales, entanglement is overwhelming and invisible because coherence is lost to the environment. The classical world is what remains when quantum relationships have become too numerous to track. This understanding removes one of the last sources of unease around entanglement. It shows that quantum theory does not undermine the reality of the world we experience. It explains it. The universe does not toggle between quantum and classical modes. It flows smoothly from one to the other as systems interact and histories accumulate. And once this is seen, there is a quiet reassurance in how complete the picture becomes. Entanglement creates correlations. Decoherence spreads them. Classical reality emerges from the balance between the two. Nothing is added. Nothing is removed. The universe simply evolves. This evolution is not driven by intention or observation. It is driven by interaction. The world becomes what it is because everything touches everything else eventually. In that sense, separateness is temporary, local, and practical. Connection is fundamental, global, and persistent. This does not diminish individuality. It contextualizes it. Each object, each system, each moment is what it is because of its particular pattern of entanglement, its particular history of interaction. Identity becomes a story written in correlations rather than a static label. There is no need to make this poetic. The physics stands on its own. But it does invite a softened intuition, one that sees stability as something achieved rather than assumed. The chair is stable because it is deeply entangled. The particle is strange because it is not. Both behaviors arise from the same underlying rules. As this realization settles, the story of entanglement no longer feels open-ended or unresolved. It feels integrated. Entanglement connects particles, shapes space-time, enables technology, explains classical stability, and anchors the arrow of time. It does not sit at the edge of physics. It runs through it. There is nothing left to chase here, only something to notice. The universe, when followed carefully, does not fracture into paradox. It gathers into coherence. Each idea supports the next. Each mystery softens as it is placed in context. Entanglement is not an exception to understanding. It is one of its deepest expressions. And it can be left there, doing what it has always done. Quietly coordinating the structure of reality, one interaction at a time, without urgency, without spectacle, and without ever needing to announce itself. As the classical world settles into place through decoherence, another familiar feature of quantum physics quietly remains underneath it all. Uncertainty. Not as confusion and not as ignorance, but as a structural aspect of how reality allows itself to be known. Uncertainty is often misunderstood as a limitation on measurement, as though particles are hiding information from us. But at the quantum level, uncertainty is not about what we fail to know. It is about what cannot be simultaneously defined. Certain properties do not exist together with perfect sharpness. Position and momentum, energy and time, different components of spin. These are not blurred because of poor instruments. They are constrained because the quantum state itself does not contain exact values for all of them at once. Entanglement lives comfortably inside this structure. When particles are entangled, uncertainty does not disappear. It is rearranged. What is uncertain for individual particles becomes certain for the pair as a whole. The joint properties can be sharply defined even when the individual ones are not. This redistribution is subtle but profound. It means that precision is not lost. It is shared. If two particles are entangled in such a way that their spins always add up to zero, then neither particle has a definite spin on its own. But together they are perfectly constrained. The uncertainty exists locally but not globally. This balance is not accidental. It reflects a deeper principle. The universe allows certainty, but it prefers it to belong to relationships rather than isolated objects. Seen this way, uncertainty is not a flaw in reality. It is what makes relational structure possible. Without uncertainty, entanglement would collapse into classical correlation. Everything would be fixed in advance, and shared states would lose their flexibility. Uncertainty gives entanglement room to exist. It also gives reality a certain gentleness. Outcomes are not rigidly preordained. They unfold within boundaries. The universe offers possibilities rather than prescriptions, constraints rather than commands. This is why quantum randomness does not feel violent or disruptive once understood. It is not noise imposed on an otherwise deterministic world. It is part of the same structure that allows coherence, correlation, and stability to coexist. Entanglement and uncertainty are not opposing ideas. They are partners. Together, they prevent reality from becoming brittle. They ensure that no part of the universe carries absolute authority over the whole. Everything participates. Everything contributes. Nothing dictates alone. This participation shows up even in the act of measurement. When a measurement is made, one uncertainty is reduced, but others necessarily increase or redistribute. The universe does not allow a free collapse into complete definiteness. Balance is always maintained. This balance is another reason entanglement cannot be exploited for control. Even though correlations are strong, they are never absolute in the sense of command. They obey uncertainty. They preserve openness. And openness in physics is a stabilizing feature. It prevents runaway behavior. It prevents paradox. It ensures that even the deepest connections do not harden into rigid constraints that would fracture causality or coherence. As this realization settles, entanglement begins to feel less like an exception to how the universe behaves and more like an expression of its temperament. Reality is precise, but not sharp. Connected, but not rigid. Structured, but not frozen. Entanglement embodies that temperament. It allows systems to share information without surrendering independence completely. It allows history to shape outcomes without locking them in advance. There is a quiet kindness in this design. The universe does not force certainty where it would be destructive. It allows room for variation, for emergence, for resilience. This does not mean reality is soft in the everyday sense. The laws are exact. The correlations are strict, but they are exact in a way that leaves space rather than closing it. As physics continues to explore these structures, the language shifts subtly. Less emphasis on particles as isolated carriers of properties. More emphasis on states, correlations, and constraints. Less focus on things, more focus on how things relate. This shift does not remove meaning from the world. It redistributes it. Meaning, in physics, has always been about what can be predicted, explained, and relied upon. Entanglement does not undermine that. It deepens it. The universe remains lawful. It remains comprehensible. It simply reveals that its laws sometimes speak most clearly at the level of relationships rather than objects. And relationships, by their nature, are shared. As this thought rests, there is nothing left to solve. Only something to hold gently. The quantum world does not demand certainty everywhere. It offers coherence where it matters, uncertainty where it preserves balance, and entanglement where connection is essential. Together, these features form a world that is not fragile but adaptive. A world that can support complexity without collapse, novelty without chaos, and connection without control. That is not a philosophical claim. It is what the experiments quietly show, and once seen, it does not disturb rest. It supports it. Because a universe that allows connection without urgency, structure without rigidity, and uncertainty without fear is a universe that does not need to rush. It unfolds, and it will continue to do so, long after attention drifts, following the same gentle rules it always has, carrying relationships forward through time, one interaction at a time. As everything comes to rest, the picture that remains is quieter than the questions that first brought it into view. Quantum entanglement began as a puzzle, a surprising pattern in measurements that resisted ordinary explanation. But step by step, through careful thought and patient experiment, it revealed itself not as a flaw in understanding, but as a feature woven deeply into how the universe holds together. Nothing about entanglement asks the universe to hurry. The correlations do not rush across space. They wait, they persist. They reveal themselves only when asked, and even then, only within the limits set by uncertainty and causality. Particles remain free to behave unpredictably. Outcomes remain open until interaction occurs. And yet, beneath that openness, structure remains intact. Shared history leaves its mark. Relationships endure. This balance is perhaps the most important thing to notice. The universe allows connection without control. It allows coordination without command. It allows coherence without rigidity. And when interaction grows too complex, it allows classical stability to emerge naturally, without breaking the deeper rules underneath. Entanglement does not overthrow the world of everyday experience. It explains why that world feels the way it does. The solidity of objects, the reliability of cause and effect, the steady flow of time forward. All of these arise not because quantum rules fail, but because they succeed so thoroughly that their finer details become inaccessible. What remains accessible is calm regularity. At the deepest level, the universe is relational. At the human level, it is practical. Both are true at once. Nothing about this requires belief or interpretation beyond what the experiments already show. The mathematics predicts the correlations. The detectors confirm them. The limits hold. The structure persists. There is no loose end demanding resolution tonight. The question of what the quantum state truly represents can remain open. The debate over interpretation can continue quietly among physicists. None of that unsettles what has already been established. Entanglement exists. It behaves consistently. It respects causality. It shapes what is possible, and once this is understood, it does not disturb rest. It supports it. Because a universe built on shared structure rather than isolated parts is not chaotic. It is deeply ordered. More ordered than intuition once allowed for. The order is simply distributed differently. Instead of belonging to things alone, it belongs to relationships. Instead of residing at points, it stretches across histories. Instead of asserting itself loudly, it reveals itself only through careful attention. That attention has now done its work. There is nothing left to chase. No paradox left unresolved at the level that matters for understanding. Only a widened sense of how gently the universe operates, even at its most fundamental scale. Entanglement does not ask to be marveled at. It asks to be acknowledged. And having been acknowledged, it can be allowed to fade back into the background, doing what it has always done. Quietly coordinating outcomes. Quietly preserving structure. Quietly ensuring that the universe remains connected without ever needing to announce how. The particles will continue on their paths. Interactions will continue to leave traces. Coherence will form and dissolve. Classical reality will keep emerging where complexity demands it. Nothing is required of you here. The physics is complete enough to rest with, and the universe, exactly as it is, will continue unfolding at its own unhurried pace, carrying relationships forward through time, long after attention drifts elsewhere. There is no need to follow it further tonight. It is already doing what it does best, holding together